Hi, this is Randy with Sophos Tutor, and I just want to say thank you for clicking on this video. Also, if you haven't already, please click subscribe to Sophos Tutor so you don't miss any of my future videos or my office hours live streams. Thanks. So what we have here are three mathematical inductive statements, and I want to talk a little bit about how we solve for mathematical induction, because the steps all look really complicated, and it can feel really confusing. But once we understand these steps, hopefully we will be able to understand mathematical induction a little bit better. So the process of mathematical induction is to prove whether a specific statement, a specific mathematical statement is true. And so in order to prove that a mathematical statement is true, for example, this first problem is asking whether the sum of these values of n, that is this pattern of n terms, equals n times 4n plus 7. We need to prove two aspects about this statement. In order for a statement to be true, we need to prove two scenarios. Okay. The first scenario that we need to solve is what we call the base case. That is the simplest form of the statement that we're trying to prove. And then the second statement we need to prove is what we call the k+1th case, assuming the kth case is true. Now, this second scenario might seem a little strange, but what it's really trying to say is that if you know that the first statement is true and that you can prove that future statements are true, then we can assume that the entire statement is true. So let's walk this back a bit. Let's first examine this first problem and break down what the statement is trying to say, and then talk about how do we prove that both the base case and the k+1th case of the statement is true. Okay. So in problem number one, we see that we have a sum Pn. And Pn consists of 11 plus 19 plus 27. And it's important to note that each term is the nth term of the sequence. So in this case, 11 is the term when n equals 1, 19 is the term when n equals 2, 27 is the term n equals 3. And so we're going to continue adding terms here. And so every term is basically 8n plus 3. That is, if I want to have an n term, I need to plug in the value of the n into this term, and that will give me the value of the term. So for example, for n equals 3, 8 times 3 is equal to 24, plus 3 is 27. That's why the third term is equal to 27. If I add all the terms from the first term to the nth term, this says that I should get the equivalent of n times 4 times n plus 7. So how do we prove that this is always the case for all n? So we need to now prove our two scenarios. The first scenario is the base case. So the base case consists of the lowest possible n that we could plug into this equation. In this case, n equals 1. So we first need to prove that the n equals 1 statement is true. That's our mission. So when n equals 1, we are simply just adding the first term, which is 8 times 1 plus 3. Okay? Now, is this equal to 1 times 4 times 1 plus 7? On my left side, this is going to equal 8 plus 3. On my right side, this will equal 4 plus 7. They are both equal to 11, and so now we have proven the base case is true. And this is typically the simple step. Okay. Now when we get to step 2, things get a little more complicated. We are going to assume that the summation of n equals 1 to k of these terms 8n plus 3 does indeed equal k times 4k plus 7. We're going to assume that that's true. So now we need to prove that the summations from n equals 1 to k plus 1 of 8n plus 3 is equal to k plus 1 times 4 times k plus 1 plus 7. Okay? So just because we've assumed that the kth scenario is true, we do not know if the k plus 1 scenario is true. So now we need to work this out. So now how do we work this out? Let's carry this over here. Well, we need to break down what this left part of the equation is. Okay? Well, the summation of the first term to the k plus 1 term, let me rewrite it here, n equals 1 to the k plus 1 of 8n plus 3. Well, this is the same as adding all the kth terms together of 8n plus 3, plus adding one additional term, which is the k plus 1th term. The k plus 1th term is 8 times k plus 1 plus 3, right? So the summation of the first term to the k plus 1th term is equal to the summation of the first kth terms plus the k plus 1th term. So this is the k plus 1th term. Okay. Now, we have assumed already that the first k terms add up to this k times 4k plus 7. So now we can now substitute this summation for k times 4k plus 7. Now we need to figure out what's going to happen with this side here. Well, let's go ahead and distribute. Let's simplify this right term here. This is going to equal 8k plus 8, but we're going to add 3 to that, so this is going to be 8k plus 11. Now, we want this to turn into this scenario here, k plus 1 times 4k plus 1 plus 7. Now, I want to break this down a little bit here, because I don't know what the inside of this term actually is simplified, so I just want to see what that looks like. This is going to be 4k plus 4 plus 7, which is 11. Okay, so we have a 4k plus 11 here, and we're multiplying that times k plus 1. So that's what we want to get this to. If we can turn this expression into this expression, we can then simplify into the k plus 1 expression. Well, I have our k, I have our 4k plus 7. Let's see if we can combine everything here. This will equal 4k squared plus 7k plus 8k plus 11. This will equal 4k squared plus 15k plus 11. I'm wondering if we can factor this. Well, this should equal k and 4k, all right? It's saying is this plus 1 and this 11? Let's see if these multiplies out. K times 4k is 4k squared. K times 11 is 11k. 4k times 1 is 4k. 4k plus 11k is 15k. And 1 times 11 is 11. So it turns out this does factor into k plus 1 times 4k plus 11, which we now know can be factored further to k plus 1 times 4 times k plus 1 plus 7. So we've now turned this expression into the k plus 1th expression here on the right side. This now verifies. So we've now proven both the base case and we have proven that the k plus 1th case are both true. Because both are true, we have now proven that this statement right here, adding the summation of all nth terms in the form of 8n plus 3 equals n times 4n plus 7. So I get that it feels really confusing, especially the second part, trying to prove the k plus 1th case. Some of the suggestions that I would provide, some tips, are when you are breaking down the k plus 1th term, you want to see if you can substitute in the assumption. Notice how when I broke up the k plus 1th expression, I tried to make the kth expression show up. By letting that kth expression show up, I could then substitute for the right side of the equation. And as a result, I could use my algebra to combine things and then distribute or refactor them, re-break up the pieces into the right side of the statement that we're looking for. Okay. All right. Let's go ahead and try the second problem. So problem number 2, we have a statement. We are trying to prove that 7 to the nth power minus 4 to the nth power is divisible by 3. So we can write that as 3 times k, where k is an integer. And you can write that as z here. We want to make sure that this is always a multiple of 3, where z is an integer. So in order to prove that this is true, we first need to look at the base case. So the base case is when n is equal to 1. So let's see if when n equals 1, we get a value that is divisible by 3. So 7 to the first power minus 4 to the first power is equal to 7 minus 4, which is equal to 3. And this is equal to 3 times 1, and 1 indeed is an integer. So therefore, we have proven our base case. Again, base cases should be pretty straightforward. Now, we are going to assume that 7 to the k minus 4 to the k is always equal to 3. Sorry, I changed up my letters here. Let's call it L, where L is an integer here. All right? Where k actually and L are integers. Let's assume that this is always true. So now, is 7 to the k plus 1 minus 4 to the k plus 1, is this always equal to 3 times some other integer? Let's call it L naught, so we separate it from L. I don't know. Let's see if we can break this down a bit. We want, for the left side, for 7 to the k minus 4 to the k show up. So I know that I can make 7 to the k show up if I take out a 7. So 7 to the k plus 1 is equal to 7 times 7 to the k. We know that. We also know that 4 to the k plus 1 is equal to 4 times 4 to the k. So at least I have my 7 to the k and 4 to the k show up just as I have right here. Okay. So now I know that this scenario is equal to 7 to the k plus 7 to the k plus 7 to the k 7 times, right? Likewise, I can subtract this by 4 to the k plus 4 to the k plus 4 to the k plus 4 to the k. Now, I know for a fact that I can pair each of these 4 to the k's with one of these 7 to the k's. So I basically get 7 to the k minus 4 to the k, and I'm going to have 4 of these pairings, which is going to leave me with 3 more 7 to the k's to go. Now I already know that 7 to the k minus 4 to the k is divisible by 3. Right? So we know that this section is divisible by 3. So now, in order to prove that the entire statement is 3, I need to ask myself, is 3 times 7 to the k, is this divisible by 3? Well, it obviously is, because 3 is a factor and 7 to the k we know is an integer. So this half is divisible by 3. And we know that two numbers divisible by 3 equals a number divisible by 3. And so we know that the k plus 1th case, this statement here, is also true. Our base case is true, the k plus 1th statement is also true, so therefore we know that our original statement here is always true. All right, let's go ahead and try the last statement. So in this third statement, we're trying to prove that 4 to the nth power is always greater than or equal to 4 times n. Well, is this always true? Well, let's first find the base case. Okay. So the base case is going to be n is equal to 1. They really should specify actually what the values of n should be. Sometimes n equals 0. Could it be n equals be a negative number? Maybe. I honestly don't know, but it should be specified in this problem. But I'm going to assume that n is supposed to equal 1. Okay, is 4 to the 1 greater than or equal to 4 times 1? Well, 4 is greater than or equal to 4. And that is definitely true. So now we're going to assume that 4 to the k is always greater than or equal to 4k, given that k is an integer. And we'll say it's a positive integer. So now, is 4 to the k plus 1, is it always greater than or equal to 4 times k plus 1? Well, I know that 4 to the k plus 1 is equal to 4 times 4 to the k. I also know that this is equal to 4 times k plus 4. Okay. Well, I know that 4 times 4 to the k is equal to 4 to the k plus 4 to the k plus 4 to the k plus 4 to the k. And we need to ask ourselves, is this greater than or equal to 4 times k plus 4? Well, we already know that 4 to the k is greater than 4k. So if we take those out, is 4 to the k plus 4 to the k plus 4 to the k, is this always greater than or equal to 4? Just trying to figure out the best way to prove it, because it seems obvious to me. I just want to make sure that we're using the proper statements. Well, we know that k is greater than or equal to 1. And so we know that 4 to the k will always be greater than or equal to 4. And if we know, and if we're assuming that 4 to the k is greater than or equal to 4k, then we know that this number is greater than this number, or greater than or equal to this number. And we'll know that 2 times 4 to the k will always be greater than or equal to 0. So I think because this statement that we know is true, we know that this statement is true, which means that this statement is true, which means that this statement and this statement are true. So the k plus 1th statement is true. We've proven that the base case is true. So therefore, we know that 4 to the n will always be greater than or equal to 4n. So I think that works out for us. So these are the principles of mathematical induction. The key here is really, when you're dealing with the k plus 1th case, is you want the kth statement to show up somewhere so that you can use your assumption. And using your assumption, you can now simplify the k plus 1th term and then try to prove kind of the rest of the pieces involving the plus 1 part of the statement. Okay. And so there you go.